take it over.
No, just want to thank folks for joining this panel. MEST Center is a funded research center, a training center actually by Nimbus Services and Air Force, and get support from OSD. We can't be more thankful for their support. Our job really is to educate and train next generation of workforce in the area of microelectronics in general, but with a lot of emphasis on security. And pleased that over the past almost 2 years, we've had more than now 6,000 participants and training that went through MEST Center. We really hope that in the next few years, MEST increase that number to 30,000. That's our objective. So we thank you for taking part. We thank you for your support as well. So Naveed, back to you.
Thank you. Thanks, Mark. Good afternoon, everyone. Our esteemed panelists and the audience. We're very excited to start the panel today, and I'm just gonna jump into it right away. My apologies for my raspy voice. I'll probably have a few coughs here and there, but hopefully won't impact our discussions. The topic of the panel is the future of electronics packaging security. So in this panel, we want to really look at the trends in semiconductor industry and OSATs toward advanced integration and heterogeneous packaging, which has its own unique challenges and security concerns. Perhaps something that is getting more attention these days as we look back and see how the US contribution in semiconductor manufacturing is down from around 40% back in 90s now to about 10%. And when it comes to the advanced manufacturing and packaging, US contribution is actually more around 2%. And these alarming numbers has triggered several programs by government, and the attention is out there. And obviously the most recent one of these programs, the bipartisan congressional support of the CHIPS Act with about $50 billion in it. So in the panel, we have invited our industry and thought leaders in the field to share their vision with us and also discuss some of the critical questions in this area. So let me just start by introducing our panelists. We have 4 panelists joining us today, and without any order, our first panelist is David Kehlet. David is a researcher at Intel, working on pathfinding for programmable logic technology. He's currently developing chiplets and interfaces to enable a new model of electronic system development. Earlier at Intel, he was VP of IP engineering, developing communications protocols, signal processing, and memory interfaces on Intel's programmable logic devices. Recently, Dave represented Intel to the US government, industry, and Intel customers and partners regarding the chiplet technologies. They have earned his bachelor and master's in electrical engineering from Stanford University, and he also holds 18 patents in the area of computer graphics and video. Our next panelist, John Allgair. Many of you from academia probably already know him. John is the science director at SRC, focused on leading artificial intelligence hardware security, packaging, and automotive electronics research. He works closely with government, industry, and university partners to advance these research topics. Formerly, he was an RF control architect at Intel. He has over 20 years of very successful digital design experience with Motorola, Freescale, Fujitsu, and Intel. John also holds 14 patents and has developed about 60 integrated devices, and several of which have shipped in high volumes. He has also worked in numerous digital system spaces and is presently in the transceiver and modem fields, focusing on the control panels of cellular platforms. He's also an expert in 3GPP standards and their applications to real-world devices. Next panelist, Jeffrey Demmin. Jeff is the Semiconductor and Defense Project Manager at Keysight Technology in Santa Rosa, California. He was previously a senior lead scientist at Booz Allen Hamilton, where his work was on heterogeneous integration programs under DARPA and also other government clients. Prior to that, he was with the STATS chip pack of advanced packaging, and he worked for over a decade at Tezera in corporate development and IP acquisition. His career began in semiconductor package design at National Semiconductor. He has also served as the editor-in-chief of Advanced Packaging magazine and contributed to the heterogeneous integration roadmap. He holds a bachelor's degree in physics from Princeton and master's in material science from Stanford. He has been in industry long enough that his patents are expired, so feel free to infringe his patents. And last but not least, we have Dr. John Allgair. John leads the Advanced System Integration and Program at Bridge here in Florida. His focus is more on providing a robust, cost-effective platforms for heterogeneous integration of silicon and photonic devices to enable a smart sensor integration. Over the past 20 years of his career in semiconductor industry, John has worked in different roles focused on business growth, innovation, bringing new products to the market during 10 years at Global Foundry, AMD, Sematech, Freescale, and Motorola. His semiconductor engineering background includes advanced packaging integration, secure manufacturing, factory design, FinFET process integration, lithography, materials characterization, and engineering management. John has also served as the SPIE Advanced Lithography Program Committee and has multiple publications in peer-reviewed industry journals. He also received his PhD in electrical engineering with emphasis in semiconductor physics and processing from ASU, Arizona State University. So again, it's my great pleasure to welcome you all. Thanks for taking the time from your schedule and joining us in the panel. A couple of quick housekeeping items and the format of the panel. We will have 3 sections. In the first section of the panel, we'll ask our panelists to basically share with us their vision and the opening remarks on the topic. Next, we'll go over some questions we have prepared for the panelists, and finally, the questions by the audience. So please go ahead and put in your questions in the chat box as soon as you have your questions ready, and we'll get to them in the search section of the panel. And for the audience, please keep yourself on mute, and if there's any technical issue, please just communicate through the chat. All right, so with that, let's start the first part. We'll go over the opening remarks by our panelists, and we'll start first with Dave. Dave?
Great, thanks very much, Naveed. You know, when I was thinking about the future of electronic packaging security, I really kind of thought about my engagement that came about because of the rise of chiplets and heterogeneous integration. And the chiplet concept is popular. You know, we use it with Intel's FPGAs, CPUs, GPUs, and it brings about some interesting situations because things that used to be monolithic, you'd have buses for control, data path, firmware download. Now these might be more exposed than they were before. They cross chiplet boundaries. They might be available on the substrate and can be more observed. Now, the second part is this advanced packaging technology is fantastic, and it can include a lot of components. You might remember that photo of our Intel CEO, Pat Gelsinger. He's holding up this Ponte Vecchio GPU that has 47 individual chiplets. And so it brings about an opportunity that didn't exist before when things were monolithic for somebody to get in there and cause trouble. So I see the future is going to be providing some strong protection at the package device level. We'll take what's available now in CPUs and FPGAs and SoCs, and we're going to extend that further up the supply chain. We're going to extend that to chiplets. We're going to extend that to substrates and bridges. And this will answer questions like, can I trust the chiplet? Can I trust the chiplet firmware provider? Can I protect IP, critical IP that's in my chiplet firmware? And the idea here is the chiplets will contain small hardware roots of trust that use public key cryptography. And there's a great example that came out of the DARPA project, DARPA Shield, that really set a benchmark for how small can you get this root of trust down to 0.01 square millimeter, which is quite amazing. And these things will perform these chiplet authentication protocols, like an example I have on the right here of you query the chiplet and it comes back with a signature, and you can verify it using public key cryptography that it is an authentic chiplet. Also, these things will work within standard frameworks. I see that the future is that we'll apply some existing protocols like SPDM and a scheme called FDO to build this device authentication within those concepts to help us make sure that we have a secure device. So next page, please. So some other areas of future work, we want to use package fingerprinting technology to authenticate devices. We might find unique packaging material features. Suppose this were thermal interface material. I just drew this drawing on the right side that shows up in as a unique fingerprint that you can observe. You could then record and say it's a fingerprint for that device. Then the future is that we'll be using data management and authenticator across the supply chain. We'll go all the way up to the silicon fab, to wafer level tests, substrate manufacturing, and then at each step as it goes down to the OSATs, the final tests and system assembly, these components and chiplets and heterogeneous integrated parts can all be authenticated as they go through the supply chain. Now, this is going to take a partnership between competitors potentially. Intel's a customer of TSMC, so it requires a partnership between fabs, between substrate manufacturers, all the members of the supply chain to really enable this secure data management. We're also going to have to develop some transparent supply chain systems. How do we link this data? How do people report the data? Does it go centralized server like I've shown here, or is it a point-to-point thing that flows down as a ledger with a component and a statement of ownership? So those kind of things have to be figured out. So I'll kind of stop there and let the other participants go ahead here. But I think this is a really exciting area that's been brought about because of the opportunity with packaging, advanced packaging, and heterogeneous integration.
Absolutely. Great. Thank you. Thanks, Dave. John Oakley.
Okay. Well, hello. I guess go to the next page. First of all, I'd like to thank everyone for inviting me. It's my pleasure, an honor to be here. First of all, I don't know if everyone knows who SRC is, the Semiconductor Research Corporation. We're a trusted scientific advisor with a vast network of industry, academics, government agents. We help build semiconductor technologies. We've been doing this for over 40 years, bringing people together and try to solve these problems. So we can go to the next page. Starting in 2019, with Department of Energy, we actually started talking about what would semiconductors look like for the next 10 plus years, and started developing some grand challenges. And we created this decadal plan for semiconductors based off a series of workshops, basically looking beyond our 2D scaling and looking at what some of these challenges are. Like, for example, we know that our computer energy is growing exponentially. Our number of devices, the amount that the power they each consume, and our world energy production is fairly linear. At some point they have to cross, and different estimates put that in 5, 10, 15 years. But that's what this document's about, and it's helping guide our vision of what the future of semiconductor research is. So we can go to the next page. I don't have enough time to go through all of it. But the question is, what do I see for security for advanced packaging? The main thing is the customers basically want security advanced packaging features with no cost, or approximately no cost. And we're going to be able to need to support devices that it could be in the field for 20 plus years. So how do we even handle that? How do we model that? How do we protect these things? Heterogeneous integration is enabling us to, as we said before, integrate these numerous chiplets, different technologies, different avenues of attack. So we're going to have all these new attack surfaces. We can even integrate approximately passive attackers or monitors in our system. So how do we know when that happens? One thing I think here is that we do use these CSVs, these through silicon vias, in our 3D interconnects, and they're commonly ignored by most of our tools, and especially in security. But looking at some of the recent work, you can actually monitor the through coupling, you can monitor the signals that are going through these devices. So how do we protect the chips that we don't even know that we have an attack or a monitor there? It's a complex question. And we do have some new technologies that are rolling out, like using RRAM for our AI hardware. It's very energy efficient. Oops, did we lose the slides? Sorry. It's very energy efficient. I'll continue to talk for a second. In the
yeah, sorry, go ahead.
Okay. So it's RRAM is very energy efficient, and it's a very novel technology, but it actually has an issue of lifetime. So as you use it, it actually degrades and its accuracy gets worse over time. And so what about attackers that actually force degradation through power manipulation, through activities, and all these things like that? And these are going to be integrated in many of our devices going forward. Even our cheapest IoT devices are going to have these products. So I see there's a great risk, and we need to invest in the future. So just some thoughts. Next. Sorry, I was a little over, but.
Thank you. Thank you, John. Thanks, I appreciate it. So Jeff?
All right, just some quick background to let you know the point of view here. Keysight Technologies is a manufacturer of high-performance test equipment. We were spun out of Agilent in 2014, which was spun out of Hewlett-Packard in 1999. So Keysight actually ended up with the original HP business of test equipment, so a legacy of over 80 years there. So Keysight is a very vertically integrated company. We actually manufacture some of the ICs that go into our products. We have a small in-house fab in Santa Rosa here. And we also design custom chips, and we also acquire a lot of COTS components. Then we assemble them on boards and various assemblies, and equipment like what's shown at the bottom there goes out the door. So this approach, we need to do this kind of heterogeneous integration of all these different types of components to get the performance required for high-end testing. You have to have better performance than whatever it is you're testing. So we really need performance there. So that's a key part of the advanced packaging and heterogeneous integration motivation. Also, though, you can see in the lower right, there's a handheld analyzer test equipment, which is enabled by this advanced packaging, such as heterogeneous integration, to miniaturize all of that. So instead of like a box or a rack of test equipment, there's something you can handle in the field. So that's the motivation for doing these packaging technologies. So none of this is unique. I mean, many OEMs do things like this. So a lot of companies have very complex supply chains to manufacture products like this, especially in the era of heterogeneous integration. So next slide. So what are the risks here? There's assortment of security threats, and I see three groups. This is not unique, but the first one, malicious. It gets the headlines where there's a bad actor targeting you specifically with tampering or Trojans or ransomware, things like that. Also, another bad actor category, inadvertent, where yes, they know they're doing something bad with counterfeiting, but they're not targeting you specifically. They're just trying to extract some more money out of the marketplace. So that's another category of security threats. But then this other category, what I call systemic threats to a secure supply chain. They're not, it's just part of the environment, part of what's going on, broader challenges. And I think we've seen in the last couple of years, all of these have become much more prevalent. And so some of the categories here: geopolitical, trade wars, tariffs, things like that, limit availability of parts. So that's a secure supply chain, meaning it's reliable. You can actually make use of it, and that's can be one of the barriers there. Natural disasters as well, earthquakes, hurricanes, floods. We've seen plenty of that, and the pandemic obviously is a major one these days. Infrastructures that can be related to natural disaster, power issues, water supply, things like that, but also human resources. That has been quite a constraint as well, throughout the supply chain. So that's affected availability of components and things. Hiring is awfully hard these days if you're trying to do that. And the last one I list there, I call behavioral, and this kind of creates chaos in the marketplace with unstable supply and demand. So this is like where microcontrollers from a distributor are similar to toilet paper in your grocery store. People think there's going to be a shortage, so they overbuy and they create a shortage. So it's things like that they're real factors in the supply chain. So I see these as maybe the biggest threats these days is these types of things, where it's really we're addressing the malicious ones. There's a lot of technology to deal with things like that, but these other ones need to be sorted out as well to create a secure supply chain. So all of that's complicated with the nature of heterogeneous integration and advanced packaging, in part because there's so many players involved. That just creates more attack surfaces, more chances for things to not work quite right on the supply chain. So look forward to talking about all this throughout the rest of the hour here.
Very good. Thanks, Jeff. And we have John Allgair.
Hi, everyone. It's a pleasure to be here. I'm going to build upon a little bit of the comments from the previous speakers. So at Bridge, we're focused on basically the secure development and integration of heterogeneously integrated systems. And from our perspective and our customers' perspective, the goal is to try to be assured that the end product is exactly what you wanted, nothing more, nothing less. And from there, can you trust the product? And as you're all aware, this is quite challenging these days with the global nature of the supply chains. And it's particularly challenged for heterogeneously integrated systems where you have components, that can come from factories all over the world. Go to the next slide. And many of the threats were mentioned by previous speakers. They begin with design, design of each of the components, right? Where you may have folks that are reusing design and what came in from the legacy standpoint. And those threats can be propagated, and additional ones can show up in fabrication and in assembly. In assembly in particular, with heterogeneously integrated systems, you have multiple components coming together, again, from various locations. And each of them brings the same risk that an individual component may have. And all those risks are coming together, as you're doing the assembly. And then as you proceed forward with the product's life cycle, you've got the product going out into the field. How do you track that product as it's in the field? What happens to it when it goes into recycling? Does it truly hit end of life, or does it get recycled and then get maliciously reinserted or inserted for profit back in assembly? Next slide. So our goal is, as we approach this, is to develop a way to have end-to-end traceability, from initial design to end of life. We're running a pilot program in this area. It's a secure digital twin for semiconductors, sponsored by Air Force Research Lab, and we have a few partners involved. And again, the goal is to initially demonstrate concepts that can be used, from the initial design, all the way through end of life. And how do you capture, significant data along the product's life cycle that could be stored, in a blockchain type infrastructure where you've got this third party immutable ledger to track the product through its development and manufacture and into the field and end of life. Next slide will go into that a little bit more detail. Again, our focus is on pathfinding and initially demonstrating these concepts. There's a lot of work to be done in this area. This slide kind of illustrates all the various points that occur from a product's life. The chain focuses particularly on commercial off-the-shelf components, and you can see as you work your way through from design to mass manufacturing to fabrication to assembly, all the different touch points that can occur. And those for each of the commercial off-the-shelf components, each die brings in those touch points as they're assembled into this heterogeneously integrated system. So once you've integrated the system, how do you ensure that what's in that system is exactly what you wanted, nothing more, nothing less? Can you capture manufacturing data along the way and store it in the blockchain so that when that system's in the field, you can reference back to that data and have some assurance that what you have is what you expected. And more importantly, you may also have a list of gaps that for data that you had that those can highlight, for the system itself, some things that may present risks. Okay.
Perfect.
And in summary, basically, again, building upon some of the comments that were stated previously, this is quite a challenge to do for a heterogeneously integrated system with components coming from all over the world.
Very good. Very good. Thanks. Thanks everyone. Really really nice points touched by each and every panelist. I mean, we talked from the authentication protocols and use of SPDM and FDOs and fingerprinting from material point that they've brought up, attack surfaces, if they are going to be passive, what are those unknown unknowns, right? That we may come up with in these new platform where we have 40, 50 different chiplets on it. And these malicious and non-malicious problems that we will have in supply chain that Jeff brought up. And obviously some of the possible solutions like the blockchain and all of those things. So obviously that definitely needs more than one panel, but we have one panel here and set up some questions. Let's start with the first question here, and I have put just two of the panelists here for a start. Others, if feel free to chime in as whenever you want it. So, question number one: what is the main requirement in your industry for the future of electronics packaging? So, Dave or John, if you guys want to take first step. Dave, you are on mute. See, you're talking, but we don't.
Yes. Hi, thanks, Navid. Yeah, I'll take a shot at this. I took this as what is the main requirement for the future of security in electronics packaging, and I think that kind of makes sense with our context here. Mm-hmm. And I really like that traceability chain that John Allgair just showed, because I think what we want to work towards in this main requirement is, can we achieve quantifiable assurance in a zero trust environment? And so this means that, we cannot necessarily know that at every point in that supply chain that things have been physically secure or electronically secure, but rather just assume that it can't be trusted. Can you still achieve, assurance that you have parts there? And this goes all the way from the die level, substrates, bridges, interposers. We want to move up the supply chain all the way to, the very first point, all the way down into deployment and end of life. We want to use a variety of authentication methods on there. We want to use cryptographic techniques. We want to examine physical phenomena to find physical fingerprints. And a lot like John Allgair was saying, we need a secure and interconnected data management system that has standards so that people can participate in this, that it's something that people can bring up and apply throughout that diverse supply chain. And I'm just thinking, that in some cases we've looked at this, that Intel in the cases of data centers or IoT devices, but imagine you could build an airplane and that every part in that airplane could be traced all the way back. You know, it might be 1 million components in the airplane that could go all the way back, and you could authenticate that they were trusted and authentic devices.
Yeah, I guess I'll touch on this. So I kind of, my thoughts were, I mean, based on some of this we're looking at for the next 5-10 years, we're moving to terahertz frequencies and beyond. And actually, this changes the physics of the way that we do our parasitic modeling. Traditional resistance, capacitance, inductance, they kind of change. And you look at fringing and the roughness of materials, index of refractions. Those are actually changing the nature of the materials, and will change the nature of the attack structures. We all know that memory is becoming a big part of every device, and it'll be customized on the edge devices. This basically, our systems right now are set up to kind of, we know what we have, but we're going to have a lot of specific and unique kind of parts that are going to integrate together. We're going to have integrating of multiple technologies, as we mentioned. And the question is, how do they play together? We don't really have a good concept of how these things are going to be secured, how they're going to interact in a great scheme of things, or we can guess. We don't really have tools for this a lot of times. And I think one thing that, from a security standpoint, I think as we integrate more, heat is still going to be there. Heat, power distribution, power delivery. We know a lot of our current attacks are in the kind of the power domain, but we also have accelerated aging. We've seen that some devices actually get heated by their neighbors to actually actively accelerate their aging and to actually make them fail faster. So there's all these new attacks that are possible in heterogeneous integration and advanced packaging we can't do today. So those are some of the requirements I think we have to solve in the next 5 to 10 years.
Yeah, agreed. Great points, obviously. Anyone else that want to touch on this from the panel? I guess the question is really, yeah, go ahead, John.
I do have one thing. The point that Jeff made about the human capital. I mean, I've definitely seen this across the whole industry. I guess they call it the great resignation, where people, students, whatever, they're choosing not to work. And we're getting more and more of that, and that's happening more and more. And I don't see this slowing down in the near future. So the question is, how do we get significantly more people, a significantly larger workforce, because we know that there's significant government funding that's going to try to accelerate the U.S. in this regard coming down the line. How do we get these people on board? How do we have a diverse workforce for that? I mean, you can look at our panel. We have, I think we're all male. We're all white. Can we be more diverse?
Yeah, I noticed that.
Yeah,
It's also not just supporting PhD researcher type, but there's the whole,
Right.
Top to bottom. You need a lot of technicians and administrative
Right.
people and all that to run these complicated enterprises. So the PhD kind of stuff is great. That's needed, but that's only part of it.
right. I would
A small
totally,
fraction, right?
I would totally agree with the workforce comments. Not only do we have a need to kind of rebuild and reinvigorate our workforce with things that are coming, there's also a need to really raise awareness, I would say, across, other areas as well, so that folks have an awareness of why it's important to secure supply chains and what that impact can be, to their lives. And I think that's very critical, as we go forward, given the dependency that so many of our industries have, on electronics.
Yeah, agreed. So we kind of touched on the last question as well here in the discussion. But so let's move to the second question. Make sure we get the time to cover all of them. So the second question to Jeff and John Allgair, and of course others as well. Do you see any security issues emerging in current and future electronic packaging, and what would be those top threats and vulnerabilities? I guess we talked about it a little bit already, but do we have any emerging or those top that are the most concern right now in your view?
I think it's kind of come up already, but I think just the variety of entities involved when there's advanced packaging, heterogeneous integration, you have chips from a whole range of sources, designers all over the world, printed circuit boards, interposers from all over. You know, they're put together in different ways, so having a coherent strategy to test, or whatever you need to do to ensure that the parts are what they say they are. It's you have 2.5D integration, 3D integration, conventional packaging, embedded packaging. It's just off it's exponential, the challenges as the number of types of components and parties involved proliferates. So I think just the sheer scope of it is one of the biggest challenges. It's not like you're get in the door one part, you know how to test it, you know your suppliers and all that. It's much more complicated. So that complexity, I think, is probably the biggest category anyway of the source of threats.
Mm-hmm.
Yeah, I would agree with those comments. Currently, the packaging industry, even it's evolved some. Introduction of heterogeneous integration, it's kind of created a Wild West situation. And with the range of components that you can consider integrating, right? If I'm taking a older component that's commercial off the shelf, I got it in die format, and I want to integrate it on an interposer, it may come with zero thought as to the security aspects of that integration. And that could range to the other end of the spectrum, where someone may have had a chance to at least think about this up front and designed a chiplet that at least had some thought process as to how when it was integrated into the system, it would establish its provenance and where it came from.
Mm-hmm.
So again, given that the broad nature there in terms of the things that are available to be integrated, that definitely creates some concerns. The other piece I would highlight that's probably another just as equal concern is having metrics for your final system, where you can make some statements that, how secure it is, what its provenance looks like, and be able to track that over the life of the system. So have access to that in real time. Right. And if someone does a bomb change to the system and you got a new part in it, how did that impact the system from a security perspective? A lot of assessments that are done today are more static assessments. Someone looks at the system, they go through everything that's in it, they're done. That's your assessment. If changes occur along the way or new threats pop up, how those threats might impact the system, may not be captured when it's out in the field. So again, having a meaningful outcome metrics and a meaningful way to track them in real time as we go forward, I think would be a great goal to have. It will take time, but it's something I think is well worth working towards.
Yeah, I'll second that. I actually at DARPA's ERI summit yesterday, there's a speaker, VP at Qualcomm. I wrote this down here. He said the lack of meaningful metrics is the most critical open problem in our field. And I think if you can't measure something, if you don't know how to measure it, you can't improve it. That's sort of basic management verbiage there. So developing some kind of metrics to define, as Dave said, quantifiable assurance. How do you measure your security? That's difficult. So I think that's an area where without those, that creates kind of a squishy feel to the field. So zeroing in on some meaningful metrics, I think, would be good.
If I could just jump in, if you're not,
mute Norman.
Would you mind mute yourself? Thank you. Somebody is on mute. Get a lot of background noise.
It's oversharing.
Yeah, it's coming in as Noman right now, so that's one that needs to be muted.
Emma, you may be able.
Emma, would you be able to mute folks?
Yes, I'm looking.
Sounds
Perfect.
like kids are having fun.
Right.
Thank you.
Right. This is Dave. Let me just jump in with a quick comment here. I think there's an issue of scale here, just the complexity of these systems that we're building and the number of different components that go into these, that the reliance on physical security, which is one of the key things in manufacturing now, is just not adequate. And so I think the matter of scale has to be dealt with.
Okay, very good. So, so Dave, I think you made the segue to our next question, or maybe the one after that, which is question number 4. But for the matter of time, let's move into the third question. And in terms of I think we have probably covered talking about the metrics and traceability and all those concepts, which are seems like to be a consensus between everyone, which is the first step. Because when you look into the security, it's a big problem. It's ocean, right? There are different aspects of it. We talk about material design, interdisciplinary fields, and all of that. But if you want, what is that first step to take to get there? And metrics and these traceability seems to be along with that. But going back to our questions now, question number 3, does the industry have the promising technologies or standards to address these challenges? And if there is anything, how can we share that knowledge and best practices across our diverse community?
Yeah, so maybe I'll start off here. So I think, yes, we have some really promising tools. I mentioned the DARPA SHIELD project before, because it kind of ties into what John mentioned about people want security for free. So the DARPA SHIELD was able to do this in a tiny amount of silicon to prove that you can have a very capable hardware root of trust in a very small area. So that kind of helps us with the technology that you can get it in there for very inexpensively. For the SHIP program that we're doing at Intel with the US government, we're developing a hardware root of trust that's available to the defense industrial base to be used on semiconductor devices, and the goal is to get it as small as possible. So that's one technology. I mentioned some protocols, this SPDM protocol as an authentication protocol of how could somebody query a device, how could the device respond. The FDO, how you would provision credentials. So I think we have a good collection of technologies and potential standards. They need to be built into a system and a framework. On the last one on how can we share the knowledge, really I think it has to be through panels, presentations, really the sharing of best practices, so that there's just really good awareness across the disciplines, because the folks in my area who are into chip design have different set of specialties than the folks who are into the supply chain management, and so that's really a gap we need to close to get this knowledge shared.
Yeah, I agree. One thing, again, this came up at the DARPA event yesterday. This can be a good use of the government, actually, to work on defining metrics and documenting best practices. There are, in spite of how it looks sometimes, looking from the outside into Washington, there can be some useful baseline work done, documentation, gathering info, and disseminating it. So this, a government focus on this. DARPA is certainly doing that. Other agencies as well throughout the DoD, even Department of Commerce, other agencies, gathering all of that input and figuring out really what matters, what's the best way to define and track these things. Once, it won't be perfect, but if there's something that's sort of known and agreed on to a reasonable extent, then the industry can really accelerate their efforts to try to meet those goals, or know how to measure and improve the metrics that are defined in something like that. So I think that's it can't just be one company or one consortium or something. It needs to be very broadly rolled out to have an effect. So you can kind of envision like the reduction of hazardous substances, RoHS. That's, everyone knows what that is in electronics. Everyone kind of adheres to that when they need to. If there's some similar security practices that are very broadly adopted, I think that would be a huge step as well.
Very good, thank you. So I'm looking at the clock as well, and about 10 minutes, and so I'll encourage the audience to put in their questions into the chat box as well. But I guess our questions are covering what they had in mind already. So let's move into the first question, which again we talked a little bit about. In your view, are we directing proper investments to tackle these security challenges? And what would be that scale of investment that is really needed for this?
Yeah, I guess I can begin since you put my name there first. I mean, as I said in the opening, I think our biggest risk is not investing in our semiconductor future, for our collective future. I mean, the U.S. and its allies need to work together to make this happen. I mean, we all know that advanced packaging is a critical need to basically for beyond Moore's law scaling. We're kind of reaching that limit now. I mean, we even see the USICA, it talks about this and it's being discussed, as Scott mentioned earlier, the chips kind of has become USICA. And that's $2 to $5 billion in immediate research needs that they're trying to identify. Still working on that, penning it out. One part of that is that the National Advanced Packaging Program, the NAPI, I guess is what I've been calling it. They're talking about like $2 billion over like maybe a 3 to 5 year period, of which probably 500 million will be in the research funding for advanced packaging. And part of that's going to need to be is the security of these advanced packaging. As a lot of the challenges that we've been talking about, I mean, that's going to should be 10 to 20% of it, and that's what we've been recommending to the various government agencies, depending on who gets this large sum of money. But we're also trying to tell our industry members this as well. That's the kind of scale I'm looking at. It needs to be significantly larger than what we're doing now. Or million here, million there. I mean, we need to be looking at tens of millions, hundreds of millions to really make a significant impact and to bring over this expertise and the workforce that we need to actually make this happen. So definitely a big challenge, and funding is hard.
Agreed. Agreed.
Yeah, I would agree. I mean, looking at this question, you know, the first answer is we're definitely not investing enough at the moment. You know, to be honest, you know, we tend to do things a lot of times after the fact, right? And in some cases after the fact can mean something really horrible went wrong. You know, how we start changing that mindset, I think it's very important. You know, maybe trying to at least agree on, you know, one common goal, you know, which might be, does your system do what you want it to, and nothing more, nothing less? And then how do you start to work towards that? You know, I think standards are important. You know, that starts, you know, starting to teach how to do it or things, steps you might take. But then moving those into, you know, things that are maybe a bit more advanced in the sense of, for each of the systems that are out there, you know, how do you have a metric for that system that comprehends, you know, its current capabilities in today's environment? You know, what can be done to improve it, you know, especially if it's a legacy type system. You know, how do you make that data accessible? There's a definite challenge there as well. You know, some suppliers will be open, others aren't. You know, and sometimes you don't find out until again after the fact, right, that something has a problem. You know, so how you work through that together is definitely a challenge. I do think that's an area where, you know, government potentially can get more involved. You know, NIST or other agencies, you know, could sponsor an activity, you know, along those lines to provide metrics for things that are in the field and things that are being developed. You know, and then realizing that there's probably going to be a spectrum in terms of what a system requires, right? You know, something that's in a kid's toy may not have any of the requirements, you know, compared to, you know, something that's going into your banking system or your power plant. So again, it's a big problem.
Agreed.
Does need more investment.
Well, I mean, I would say, I mean, you brought up a good point about the kids' toy. We have a lot more connected devices now. I mean, the whole Internet of Things concept. And if we think that these things are not important or don't need to be secured as much, what if a kid's toy has been brought into a place that is secure, like to the bank, to the hospital, and basically takes down the hospital? Is that possible? Of course it's possible. The question is, how do we protect those devices and prevent these kind of things in the future? And it's hard. And I don't think there's any good solutions yet, but it definitely needs a lot more research and funding to make this happen.
Yeah, I agree. And there are a lot of knowledgeable people out there too, right? It's just how do you coordinate it?
Very good. So we'll probably try to keep the last question a little bit shorter answer so that we can get to some of the questions from the audience. Any advice, and the question is to all panelists, you can give to the academic community in terms of how they should support these efforts?
I mean,
yeah,
who wants to go first? Sorry.
Maybe I'll just kick this off. So I would like some ideas on how to reduce the silicon investment, the design investment, to perform this, these security operations like authentication. One of the really interesting capabilities is this PUF, the physically unclonable function, but it's very difficult to port it and it's expensive IP. So some way to make this maybe an all digital IP. Some way to reduce both the design investment and the recurring costs in die area.
I mean, I think from my perspective, I think the metrics are definitely what we need to be able to measure it to actually justify any cost that is associated with any of these security features. If we can't measure it and we can't say how much it benefits you, then we'll never be able to afford the cost. The cost has to be zero or approximate zero. But I think probably the biggest issue that we need is we need a lot more people in the field, in the semiconductor field. We need a lot more researchers. We need a lot more headcount. We need more thoughts, more diversity. I mean, I would love to have seen a female on the panel, or you know what I mean. But I don't see that too often, and that's something I think we definitely need to fix, because we need to have more diverse thought. We need to have more people, just more. And yeah, that's across the board: bachelors, masters, technicians, PhDs, and I don't have good solutions yet, but that's what we need.
Now, one bit of advice I might give is it'd be good for academic researchers to work with companies. I imagine that's pretty standard approach, but I know from the government side that can be an appealing proposal from a team that has academic and industry partners. The academics can maybe go as Darcy. Maybe the academics can work on things that maybe there's not quite the expertise in whatever company, and vice versa. The academics can get insight from the company on how things actually work out there. So a team like that, I think, is good rather than either just operating in a silo. So that's a way to increase your chance of getting government funding.
Yeah. The other thing I would highlight, would be trying to work some of these concepts into the core program area, right? So, if you've got basic math and science that you have to take regardless of whatever your major is, again, trying to work some of these concepts into one of those core programs to raise overall awareness for folks. Because again, I do think that is also one of the industry challenges, is that a lot of folks, quite frankly, unless they read it in the news, they may not be fully aware of some of the vulnerabilities that might exist around them. So first step, raise awareness, that can maybe then raise support.
So I'll get into some of the questions by the audience. Perhaps it's a good one to connect to this question number 5. So Walid has asked, from your perspective, we seem to train a lot of our students on circuits, but very little is done on chip package, board co-integration, And if you have any suggestions how to improve this, I guess that's a question to the academic people as well, but definitely your vision and perspective.
I think it's definitely a shortfall. I come from the packaging world, and it's historically less technical than the process or the circuit design, but that's different. That's a generation ago. Now it's just as technical. So I mean, at some level, as time goes on, there will be people who have PhDs and become professors with background in packaging and can relay that to the next generation. But that's slow. So I don't know if that might be a good, that's workforce development type of activities already going on in the government to elevate the profile of packaging. So I think that's happening. Otherwise, it's sort of an evolutionary process, it seems like, unfortunately.
Well, maybe I can put my 2 cents in here. I mean, I think we've definitely focused on making small things secure, little designs, little circuits. We integrate many of them together, and then the sum of these little pieces, even within the chip, creates new vulnerabilities that we didn't expect, new avenues of attack, of monitoring, just new failures. And going from integrating those to going to the next level, all it is an expansion of that. It's just geometrically more complicated than it was before, because now you're going to have all of these potentially where we have little secure pieces within them into a little box that is less secure. Now we're going to make many of those together into a system that we can't even trust all the devices in there, right? How do we then protect any one device if we can't trust all the devices? Even if we could trust all devices, now the interconnection between them, the interaction between them could create new vulnerabilities, because we don't really test our systems in those ways. I mean, we test them in the field, we test them in products, but we don't really simulate them. We don't do exhaustive simulation testing of what, let's say, what a whole iPhone would look like. There's no computer that exists that could do that in a reliable fashion. So, yeah, it's just hard to handle and hard to scope, and it's just going to get worse, exponentially worse over time.
Absolutely, yeah. Thanks, thanks, John. So it's 101, and we don't want to keep the panelists and the audience more than that 1 hour. I keep getting questions, and perhaps we can get a promise to have the panelists again for another one to continue the discussion. But as a very quick summary of it, I guess the really good points mentioned about the diversity, the metrics, reducing the silicon investment, and all those aspects are important items to look into for the community, for industry, academic researchers, and so on. So I want to thank again from the panelists giving us their time, joining this panel, and audience too, to join this panel. And with that, I guess we'll close this one. And if there are no other last words from the panelists, we can close the session.
We need to work together to make this happen. Right?
Absolutely.
And I think we have a lot of divisions among our industry, among the universities, and to really solve this, we're going to have to all work together. We're going to have to collaborate. We're going to have to make a joint future. We can't just be all individual companies. So that's my last thoughts.
Yep, agreed.
Agree.
And I guess, John, it all goes down to that investment that you mentioned, right? I mean, it reminded me when we talk about the CHIP Act's $50 billion, and then a couple of months later, Taiwan talks about $100 billion. And then a few months later, South Korea talks about $450 billion. Then we do see the scale, right? And it keeps me up at night when we think about when we were getting some of the equipment in our lab. We were seeing and hearing from those engineers who were in the installation that year them selling only a couple of those equipments in US, while they were selling more than 50 or 60 in Asia and out of US. So without having that big crowd, it's a very complex area and it's difficult to get there. All right. Thanks everyone. Thanks for the great discussion. I appreciate it. Looking forward to see you guys again, and enjoy the rest of the day.
Okay,
Thank you.
Everybody.
Thanks, everyone.